Okay. Let's now move to the first part of our discussion on detector applications, which are gaseous detectors. What are these? We'll discuss operating principles. We need to look a little bit at how charged carriers diffuse and drift in a gas. We'll have to talk about primary and secondary ionization and the choice of gas parameters and gases mixtures that are conventionally used in gaseous detectors. Gaseous detectors have various applications separated coarsely in terms of their operation modes. We can have ionization chambers that record the signal of ionizing particles without amplification. We can have amplifying modes that are proportional to the incident signal, or we can have an amplification that's so strong that it actually plateaus and we are operating the gaseous detector in counting mode. And at the end, all these different ingenious ideas lead to a large array of detector applications of varying utility. Generally speaking, looking back at 50 years maybe of detector development, gaseous detectors were the earliest, but have been continuously replaced by other detectors, most notably silicon detectors, because silicon industry has of course gained enormous traction. However, for very large detector volumes, they still are advantageous and price-worthy. So let's look at operating principles of gaseous detectors. The defining feature is that somewhere there's a gas and a particle is going through, and we can think of a muon. It's not important what it really is, but we think of a muon, and this ionizing particle causes a primary ionization according to Bethe-Bloch equation along its track. Here I put a sketch of a wire detector. So somewhere in the detector will be an anode and somewhere a cathode. The electrons drift to the anode. The ions that are produced in the ionization drift to the cathode. In this particular cylinder symmetric configuration, the electric field is proportional to 1 over r, as I hope you know, from the electrodynamics course. So the charged particles, muons for example, penetrate our gas volume, and along the track they produce electron-ion pairs. Okay. The high mobility of the electrons and the ions makes these detectors ideal for large volumes. We'll see that electrons can travel with kilometer per second speeds, and if your readout time scale is in the nanosecond or even microsecond regime, that's enough to completely read out the ionization signal. Now, the simplest detector, as is shown here, consists of a gas filled volume and an anode and a cathode that's on a different potential. So for practically all gaseous detectors, high voltages are involved for separating the charged carriers. Here we have a wire detector. Not all gaseous detectors are wire detectors. Wires pose some advantages. One can have avalanche formation, but they also have disadvantages. Namely, they can lead to disastrous malfunction. If a wire breaks in a large detector volume with many wires, the whole detector can be broken. But the wire leads to the possibility of amplifying the signal, because the electric field, because it's 1 over r, can become very high if the radius of the wire is thin enough. If the electric field is high, the energy of the electrons as they approach the anode wire can exceed the ionization threshold, and secondary ionization can then multiply the signal. In this way, we can actually go down to single particle detection with ionization coming from incident ionization signals from detectors in the millimeter and centimeter regime. So we can detect single particles. Now, let's look at a few basic parameters of the diffusion and drift of electrons and ions in gas. In the absence of any external field, you have electrons and ions, and those move uniformly away from the point of creation just because of Brownian movement. Of course, gas will have a temperature, and if you create by your incident signal electrons and ions, those will diffuse. One needs to solve the Boltzmann equation, which is done in Kolonowski. We don't have to do it here. I only want to give you an overview of the orders of magnitudes that are involved here. The diffusion velocity is a function of, is proportional to the square root of the temperature. If you insert the numbers, because of the large mass difference that appears here in the denominator, electrons have a very high diffusion difference, diffusion velocity of 10 micrometer per nanosecond. Now, a micrometer is not a large distance, and a nanosecond is not a long time. If you put in the numbers, that's 10 kilometers per second. That is, in our classical world, a very high velocity. Ions have 2 orders of magnitude less. So we're talking about tens of meters. And that's the diffusion. That is without applying any electromagnetic field to the detector. The diffusion coefficient, so-called diffusion coefficient, is determined by the average free path, which we call here lambda. Don't confuse it with the interaction length. So the average free path length, lambda, of electrons and ions in the gas appears as a multiplying factor with the velocity of diffusion to give the diffusion coefficient d. And the diffusion coefficient d enters the solution to the Boltzmann equation for an initial point-like ionization deposit. Why am I talking about this? Because I want to give you a feeling about what happens to a small ionization deposit somewhere in the detector. So imagine you get a particle that hits a small gaseous volume and induces a point-like ionization deposit. The solution to the Boltzmann equation is a time-dependent Gaussian, and from the exponential here, we can read off the spatial extent, the spatial width of this Gaussian is proportional to the square root of t. So if you have an initial deposit, just by means of diffusion, this initial deposit will dissolve into a Gaussian, and the size of this Gaussian will grow with time with the square root. Similar formulas are valid for the volume. Now, if we apply an electric field, this initial Gaussian will move along the electric field and increase in size according to this Gaussian behavior I just discussed. So that's the situation for an incident point-like ionization deposit somewhere in a gaseous detector. Now the drift caused by the electromagnetic, in this case only the electric field, is superimposed onto the diffusion movement. Now in principle, this would cause an acceleration. The deposit would move faster and faster. However, the acceleration is interrupted by the collision with the gas atoms. So we are here now dealing with ions and electron movements in a thin, or maybe not so thin, gas, and collisions limit the drift velocity. The mean drift velocity, these are all empirical formulas, okay? The mean drift velocity is typically written as a mobility times the electric field. However, the mobility itself depends on the electric field, so that's a nonlinear relation. For small electric fields, the mobility is almost independent of the electric field itself, and so we get the constant. So we get a constant relation between the drift velocity and the electric field. So drift velocity and diffusion velocity play together to define the dynamics of the movement of that ionization cloud. So the diffusion makes the initial deposit, it widens it, and the drift velocity moves it along. And you better make sure when you design a detector that the drift velocity is large enough so that the initial deposit can hit somewhere a sensitive detector element before it has completely diffused, because otherwise you completely lose your spatial resolution in the detector. Typical values are for the drift velocity are in the 10 to 100 kilometer per second regime. So the drift velocity can be chosen much larger or larger than the diffusion velocity is. Two more comments here. First, the drift velocity is very roughly inversely proportional to the pressure. If you raise the pressure, you have more gas molecules in the path of the ions and the electrons that are drifting, and so the drift velocity will be lower. On the other hand, we've also seen, I did not spell it out, but we've also seen that the diffusion velocity, that the diffusion coefficient via the average free path depends on the pressure. However, it only enters with a square root in the evolution of the width of this initial deposit as a function of time. So the pressure is one of the design, well, once you've built the detector, once you've designed the detector, you design it around a certain pressure value, and at the last step, the pressure is something that can be adjusted without the detector geometry. At the last step, the pressure that the detector is operated with is optimized. Small comment, in most of the detectors, in particular when they are large, when they fill large volumes, they will be subject to inhomogeneities in the electric field, and there will also be magnetic effects present. Most of high energy particle physics detectors use magnetic fields for the momentum measurements, and those can hardly be shielded. So if there is a magnetic field, for example, if it is parallel to the electric field that's shown here, then the charged ions and the electrons will not drift along straight lines, but they will drift in spirals, spiraling around the magnetic field lines. The spiraling frequency is the cyclotron frequency that we've derived in completely different context, namely in the collider physics lecture. And the drift velocity will reduce. The formula is given here. We will not use it, but it has to be kept in mind when designing detectors. Now, ionization in gases. The last lecture I've spent a long time in discussing the stochastics of ionization, and I'm sure you've wondered why I did that. And here's the reason. We have now a cathode and an anode. In this example, it's sketched to the left. There's no wire. It's a different example to show you how gaseous detectors can look like. The readout is at the anode. So the readout is the electrical signal read out from the voltage difference between the cathode and the anode. And let's look at the particle that's going through here. Now in blue dots, that's just schematics. The blue dots are the primary ionization. So look at this track here, for example. That's a real life image from the CERN bubble chamber. So here we have electrons, and we discussed delta electrons, which are secondary ionization, because the energy transfer for head-on collisions with very small impact parameter is only limited by the incidence particle energy. So we can lose occasionally, with a low probability, but occasionally we can lose a very large fraction or a sizable fraction of the particle in one of these collisions. The resulting electron energy that's kicked out from somewhere of the atomic shells of the gas can then cause secondary ionization. And the secondary ionization can be very important. Now, the big sketch here shows a very large detector volume. You have here a track that's going through, and you see here many secondary ionizations. The total ionization yield of such tracks in such large detectors will be very Gaussian, because on average, they all look the same. However, if you zoom in and if you imagine you make your detector small, then sometimes you will see actually secondary, you will see plenty of secondary ionization coming from delta electrons, and sometimes by chance this will not happen. So that's how the Landau distribution and the stochastics of these delta electrons would reduce the achievable energy resolution for small detectors. For larger detectors, that's less of a problem. Let's talk about the total ionization yield, because obviously not only primary but also secondary ionization will contribute to the total ionization yield in the gas detector. I put an example here. We have many more examples on the following and on the next slide. Argon is a frequently used gas under normal pressure. Gas volume of 1 centimeter, the EDX is 2.44 kiloelectron volts. So an ionizing, that's the energy that an ionizing particle loses. That's a minimum ionizing particle. So it creates, on average, 29 electron ion pairs. And that means actually you have 33, you think you have 83 electron volts per electron ion pair. However, secondary ionization is a factor of 3, raising the number of electron ion pairs from 30 to roughly 90. So secondary ionization can be a factor 2, 3, and more above the primary ionization, such that in this particular example, the average energy to create an electron ion pair in the detection volume is only 26 electron volts. Remember these ballpark numbers. So it takes 20, 30 or so electron volts to create an electron ion pair. We'll in the next lecture talk about semiconductors, and in semiconductors, this number is much lower. So in gaseous detectors, we have a fairly high minimum energy required to create an electron ion pair. It's not 80, it would be 80 for primary ionization, but because of secondary ionization, it's only 26 electron volts that are needed to create such a pair. Now let's make a ballpark considerations of what gases to choose. The optimal gas will of course have a high ionization density. We know from Bethe-Bloch that this is proportional to C. It should have a low rate of multiple nuclear scattering. That would be what we discussed in Molière theory. If the rate of multiple scattering is high and it's proportional to C squared, then the spatial resolution degrades. Helium, for example, is on one end. It has a very low multiple scattering because C squared is comparably low. It has a large, however, it has a large radiation length and a correspondingly low ionization density. On the other end of the nucleus of the nuclei is a xenon, where exactly the opposite is true. So there you have a high so you have a completely different relative contribution of ionization density and multiple scattering. In between is argon, and argon is a frequent compromise between good ionization density, where you favor high C materials, and low multiple scattering that penalize high C. Good. The high C materials like xenon do have an advantage though, because the pair creation grows with C squared, they are very photosensitive. So sometimes it is possible to create a gaseous detector that detects photons, and the photons cause pair creation, and the pair created electrons cause the ionization signal. So these very high C materials can be used as add-ons to the gas to make them photosensitive. Here we show gas parameters. The table is taken from Kolanowski. Argon is here. We have 29.4 average primary ionization ionized electron hole pairs per centimeter of a minimum ionizing particle, and the total number, that's what I talked about, the total number of electron hole pairs, including secondary ionization and delta electrons, is roughly 3 times higher. For the low C materials that are at the top of the table, this ratio is a little bit lower. For helium, it's only a factor 2. And for the high C materials, this can go up to, for xenon, this can go up to a factor of 10. So if you had used xenon, for example, primary ionization is actually, it's almost negligible as compared to secondary ionization. Other important gas parameters are listed here. DME is a commonly used gas because it's cheap. It is dimethyl ether, something that I always forget. That's why I wrote it down. Argon, krypton, and xenon are extremely expensive. Good. Now we've talked about the basics of gas detectors with respect to in hindsight of what we discussed in a previous lecture, the interaction of particles with matter. Let's now look at the basics of the operation mode. First of all, an amplification factor is defined as the ratio of the collected electrons at the anode wire to the number of primary electrons that were created in the ionization process in the gaseous detector. The plot to the right shows the number of electron-ion pairs that are accumulated as a function of the voltage that's applied in the gas volume. We don't even say whether this is a wire or whether this is a detector without wires, maybe only consisting of strips or plates. And therefore, please don't take that too seriously. This is only very exemplary. That's good enough. We only want to understand the basic operation modes. Now, if the voltage is very low, parts of the electrons and the ions that are created will recombine. If the voltage is 0, all of them will recombine at the end of the day. This is what's happening in air. Charged particles, the muons from the cosmic showers, pass through, they make an ionization signal, and with a and more or less instantly recombine. So if the voltage is too low, the electric field will be not strong enough to separate electrons and muons, and we will see nothing. Above a threshold, above a certain threshold of here for this detector example, is probably 30-40 volts or so. It's enough that separation takes place, but there's no amplification. So we collect the primarily produced electrons and ions at the anode and the cathode, but only those particles, only those charged carriers are collected. This is a useful operation mode for dosimeters, for dosimetry, and for flux measurements. However, it's usually not enough for detecting single particles. If the voltage is increased, one enters the regime of proportional counters. Proportional counters are the proportional mode. Here we have to think of a wire detector. In the vicinity of the wire, inside a wire detector, the field strength, of course, linearly depends on the voltage. However, the regime where the ionization energy is lower than the energy provided to the electrons from the electromagnetic field increases, and hence an avalanche can be formed. We'll discuss about avalanche formation in a little bit. Now, for a moment, please take my word for it, that we can get a factor 1,000 to 100,000 as a multiplication factor in avalanche production. It's important to understand what is proportional here and what is exponential. It's a proportional counter because while an avalanche develops, if you have twice the number of primarily ionized electron hole pairs, you'll get twice the signal. The exponential characteristic is with respect to the voltage that is applied. If you apply, if you increase the voltage by a constant amount, the zone where an avalanche can develop increases by a constant length interval, and that will allow you to take one more step in the avalanche, and hence a constant factor on the gain, and hence we have an exponential growth with the voltage. Still, this is proportional with respect to the incident ionization signal, and therefore this is the most important operational mode in particle physics experiments, as long as we want to measure the total ionized energy signal. Now, if one increases the voltage further, there is an effect of limited proportionality. That is because in the avalanche development, a great number of ions are produced, and these ions of the opposite charge, they are close to the anode wire. They can shield the electric field, and they do shield the electric field, and that causes a nonlinearity. If you look to the diagram, in fact, the exponential curve would increase even more steeper than is happening in reality in the region of the limited proportionality. So this creation of a large number of ion pairs close to the wires that shield the field strength causes an attenuation. Although it can be hardly seen because it still raises, but it doesn't rise quite as fast as it did for lower voltages in the proportional regime. And then for even higher voltages, we are in the saturation regime. The signal becomes independent of the primary ionization. A single particle will create an avalanche. The avalanche will be large. It will shield itself, and eventually the recorded number of electrons will be completely independent of the incident particle's ionization deposit. We are in counting mode. A spark forms, for example, in the detector, and this is called the Geiger operation. We all know Geiger counters, I think. Geiger counter is precisely that. You take an incident ionization signal creates, through an avalanche, it creates a spark that then discharges. The electrodes become connected by what we call a streamer, which is an extended avalanche that forms in the direction of the electromagnetic field, and the electrodes fully discharge. Now, the discharge has to be stopped because otherwise you just have a spark, and you get a large electricity bill, and eventually your detector will melt. That's not useful. However, still at the time scale of where we do our detection, this means that such detectors will have a very, very large dead time, because it takes a while if such a streamer and a plasma flux tube has formed, a very high number of charge carriers are present in the gas. Good. Now, these are the operational modes of a gas detector. Let's look at the important ones. Let's look at the signal formation. Now we talk about an ionization chamber. We don't yet talk about avalanche formation, okay? So we have a particle, an electron ion, we have a particle creating an electron ion pair by means of the Bethe-Bloch energy deposit. And now we ask, what is the signal that we record? Let's look at typical numbers. So let's say this is a detector 500 volts per centimeter. That's a planar ionization chamber. Here we are, for 500 volts, we are actually, the sketch shows that we are in the proportional counting regime, but that's only true for detectors with wires. If it's a planar detector, in fact, with 500 volts, we cannot enter the regime of avalanche creation if there are millimeter or centimeter distances involved. So we have 500 centimeters. Let's say we have 10 centimeters of drift space, and running the numbers on the previous slides gives us 2 microseconds for the electrons and in fact 1,000 or so more for the ions. Difference is always between a factor of 100 and 1,000. In short, the electrons are very fast, very high mobility for the electrons, and very slow mobility for the ions. Ionization chambers aren't used in high energy physics a lot. They are used in the nuclear industry. The reason is simply that with an ionization chamber, it would have to be very large to detect single particles. We need very roughly 1 femtocoulomb as a minimum charge, such that our amplifiers can see a signal above the noise. So we need something that amounts to something like 10,000 or so electrons, and hence usually we need some sort of amplification. 10,000 electrons created by primary ionization would just be a very large detector. Still, the ionization chambers are important to understand the signal formation, and that's what we are doing now. So listen up. The top row here shows the currents produced by electrons and ions. We have an electron ion pair created in a distance x from the anode. The electric field points to the cathode, and now the electron moves to the anode. It does so very fast. Now the question is, and it's an important question for detector design, when is the signal recorded? It's a common misconception that the current consists of electrons. And if the current would consist of electrons or of charge carriers, actually you could argue that the current is, the signal is created when the electron is absorbed at the anode. But that is not true. The point-like charges, which are the electron and the ion, they are surrounded by electric field lines. And those electric field lines, they extend all the way to the anode and to the cathode. And this can be calculated with Gauss law. if you move the electron towards the anode, of course, the field lines extending to the anode will have a ever larger impact, and they will start to push around the electrons at the charge carriers inside the, for example, the metallic surface. So the current starts to flow immediately. Also in electrodynamics, the current is given by the movement of the charge carrier. It's not created by the appearance of the electrons at the anode. This is the Shockley-Ramo theorem, okay? The current, the signal starts instantaneously once the charge carriers produced by the ionization signal begin to move by means of the electrical field lines extending through the whole gas detector all the way to the anode and the cathode. So let's say the drift velocity of electrons and ions differs by a large factor. That's the first thing we say. The second thing we say is the mobility of the electrons is much higher. Then the current that we measure is constant until the electron hits the anode, and then it is over. Okay? Once the electron hits the anode, the current associated with the electron has flown. Similarly, for the ions, it's the exact same story with a different charge and with a different time scale. The electron current flows with a factor of 100 to 1000 faster than the current that's induced by the ions. If we put this together, the total charge that we measure, this is the measured total charge as a function of time. It raises very quickly while the electron moves, and then it moves, and then it raises slowly while the ion still moves. So that steepness here is given by the electron plus the ion charge, because the ion moves in the opposite direction. The total accumulated charge that we measure is positive, and then the electron has reached the anode, and then the ion still drifts. The steepness of these two shapes here of the total charge that we measure differs by a factor of 1000, or 100 to 1000. So if let me try to sketch this, because we're going to use it for the avalanche formation. If this distance of x is small, if the ionization signal happens close to the anode, what you're going to have here is a charge collection that extends very long in time. If you have the creation very close to the cathode, then you collect your signal very quickly. That's an important point for the dynamics of the movement of the charge carriers in gaseous detectors, and not only gases, also silicon detectors in all the detectors. And now all we have to do is assume that the ionization deposit is constant across the particle's track, and integrate one. So if you integrate the currents for different values of x, you'll get the triangular shape. In the beginning, the current is maximal because the whole ionization signal still moves, and then electrons begin to be absorbed at the anode, and that reduces the current, and that's why it drops. And the total measured charge, therefore, increases with a simple quadratic function. There's no need to derive it. I'm sure you know that if you can imagine that if you integrate this formula these currents for that depend on x over x, you will just get a linearly falling current because the electrons and the ions are subsequently absorbed, and hence the total measured charge is a quadratic function of the time. Bottom line, and that you must know, Shockley-Ramos theorem, the current that flows instantaneously starts with the movement of the ionization signal, the electrons and the ions. It stops, it has flown once those guys have reached the anode and the cathode. That's a common misconception in all detector applications. Good. Now we know how an ionization chamber works and what's its time dependencies. Let's look at more high energy physics applications. We now talk about the proportionality mode and signal amplification through secondary ionization. And that secondary ionization is not the ones by means of delta electrons. This is the secondary ionization by means of avalanche formation. So let's discuss it. The electrons in a strong field can acquire enough energy to create secondary electron ion pairs. The amplification factor in gas detectors operating in this proportionality mode is roughly independent of the primary ionization, and hence the signal is proportional to that primary ionization. And we can achieve large gains of 10 to the 3 to 10 to the 5 and 6. And because our minimum threshold to record a single particle is 10,000 electrons, this factor is immensely helpful and allows us to detect single particles. Moreover, if you know the momentum of the particle from a different measurement, maybe in a tracker, a silicon tracker that we'll discuss next time, then you can use the EDX measurement to identify the particle, because we know that the EDX depends on beta gamma, and beta gamma is if you have beta gamma and you have P, you can compute M, and the mass M identifies the particle. The limit of the proportionality mode is reached when the ion cloud that's produced in the avalanche formation begins to shield the electric field, for example, around the wire, or modifies the electric field that's present in the detector locally and leads to nonlinearities. If the field is shielded, you have high ion densities, then electrons and ions can begin to recombine, and other atomic reactions may take place in the gas, and then photons are created. Now, if photons are created because of recombination in your gas, it's very easy to come into trouble, because that photon can hit, for example, the copper electrode. Somewhere will be other metals somewhere in your detector, and the photon can traverse the whole detection volume and can end up anywhere. And if it happens to hit some atom from a gas impurity or a metal electrode, it can release further electrons and at a later time trigger secondary avalanches. So photons in the detector are limit its operation, and hence usually the gas is mixed with a so-called quencher. A quenching gas is mixed to it, for example, methane or CO2. Those molecules are highly effective in absorbing photons. That's the purpose. Let's look at typical geometry that's used in proportional gaseous detectors, we can build a wire detector from a cylindrical cathode and a thin central anode wire. Now look at the electric field as a function of the radius, okay? Let's say the most important, the most important design element for a wire detector is the radius of the wire. Let me use my pen. Let me highlight in red. The calculations are trivial. I don't switch here. First of all, we've discussed, and I think you know that the potential in the vicinity of a cylindrical in a cylindrical configuration with a wire at the origin is the logarithm of r. If you differentiate this, E becomes, oh, I don't know why again do I have an E? E then becomes proportional to 1 over r. Let's say we have a wire with a thickness of 10 microns and a detector with a cylindrical detector with a radius of 10 millimeters. In this particular case, we can now assume that below a critical radius of 1 micron, the field strength is large enough for secondary ionization to be created. So we define the critical energy as the energy below which the field strength is large enough that secondary ionization takes place. So very close to the wire avalanche production starts. Let's keep this in mind when we look at the avalanche production and the signal formation close to the wire. I need to erase this. How does this proceed? Electrons are produced by the primary particle drift towards the anode wire. So let's say here came through a muon. It created a single ion-electron pair. Now the ion at this time scale actually stays in place. It moves with a drift velocity that's a factor at least 100 less than the electrons. The electron approaches the wire, and below the critical detector dependent, material dependent, gas dependent threshold, it begins to form secondary ionization. So here it has an energy that's high enough to ionize further gas molecules. So you have one more electron, and then this process multiplies until a cloud of electrons and ions forms, and these electron and ion clouds then separate. So after a short while in this avalanche formation, we have a slowly moving ion cloud from the avalanche and a slowly moving ion cloud from the avalanche and a quickly moving electron cloud. Those slowly separate, and because the diffusion and drift velocities of the electrons are 2 orders of magnitude higher than for the ions, the electrons very quickly diffuse around the anode wire, and then they are absorbed very quickly. Hence, on a factor that's on a time scale that's a factor 10 to 100 faster than the ion movement, the electron signal from the avalanche is absorbed is absorbed in the wire. Now, now the electrons are gone, the ions are still in place, but they have been created very close to the anode. So they now traverse the whole detector until they reach the cathode. That means the signal is almost entirely due to the ions. That's just because the electrons are created so close to the anode that they are absorbed almost immediately. Now, with this picture in mind, let me go back to the previous discussion. So think of plenty of electrons being created very close to the anode. That means actually we have a deposit. We have deposits in this sketch that look like this. The collected charge of the electron happens very, very quickly, and then the ions drift and cause the accumulated charge signal, okay? That's why in wire detectors with amplifications in the proportionality mode, the signal is almost exclusively given by the ions. We can calculate this. We can take the ratio of the potential energies that ultimately cause the signals, call this V minus over V plus, and insert the numbers. Assume that you have an electron-ion pair created at close to the critical the critical field strength will be a critical radius, which we assume to be 1 micron away from a diameter of 10. So at a distance of 11 microns from the origin, we have we begin to create our avalanche, and if you insert the numbers, the electrons will contribute with a factor logarithm of 11 over 10, while the ions, because they go, I mean, they're created at the same place, A plus R crit, but they move across the whole detector, and that distance in our example can be arbitrarily large. Here we chose it to be 10 millimeters. So a diameter of 2 centimeters. And if you insert the numbers, you find that only 1% of the collected current is due to the electrons. 98.6% are created by the ions. Okay, so now we understand the formation of an avalanche signal and its approximate time dependence in a cylindrical wire detector. Let's look at something else, drift velocities and the gas choices. We had just discussed the 2 centimeter cylindrical detector. Gas detectors can be much longer, and one can exploit that the drift velocity of electrons and ions is under good control for good timing measurements. To that end, gas choices are an important way of defining the operation characteristics of a gaseous detector. Now you want, of course, a high signal. So you need a high ionization density. Looking at the ionization density, you want noble gases, argon, krypton, or xenon. As we've seen, xenon can be used even for photodetectors because it has a very high pergration probability. One can also use Cu2, CF4, or DME. A thing to avoid are electronegative gases. If you have oxygen contamination, oxygen can capture electrons, and if you have a single particle, if you have a number of primary ionizations that's low, then you can accumulate inefficiencies because the single ionizations can then be captured by oxygen. So typically, it's not always true, but typically, electronegative gases are to be avoided because they attenuate the signal and they can completely kill it in case the detection volume is small. Argon is a good compromise between low multiple scattering and low multiple scattering favors low C, as we've discussed, and a high ionization density that would favor high C. So there is no perfect world. I mean, maybe there's a perfect world, but there's no perfect gas in that perfect world. A good compromise is argon. The pure noble gases, however, cannot be operated stably because those pure noble gases, they do not absorb photons. I briefly mentioned photons before. Here's an example. If you happen to have a large ionization signal or a wire detector with avalanche formation, then the pure noble gases will recombine and de-excite, produce, for example, in this example, argon can de-excite to yield a 11.6 electron volts photon. That photon can hit an copper electrode that's somewhere in the detector. That energy is only 7.7 electron volts, and the photon doesn't lose anything. The photon will, an 11 eV photon, can just pass through the whole detector, hit the electrode, and release release a new avalanche. So release an electron that then creates a new avalanche. And that can happen later in the game, after you've read out your signal, because this electrode can be anywhere in the detector, and hence it's not possible to operate the gaseous detector purely with noble gases. So one needs to add molecules that absorb the photons. Those are called the quencher gases, as we've discussed, briefly at least. And the characteristic features of these are a broad absorption spectrum. So here we have methane, for example, ethane, and isobutane. I hope I pronounced these names correctly. And what you see is the drift velocity. Let's look at the plot, the top right plot here. That's a good example. You have pure argon and you have the drift velocity versus the electric field. Never mind, it's normalized to the pressure, but that's not important. So we have a drift velocity of pure argon, and now we increase. Now we increase a fraction of methane, and this leads to an increase in the drift velocity that's also non-linear. But that's desirable because we can now take our desired field strength, and let's say it's here around 0.15 in these units. So we are here for the electric field that we want to operate our proportional detector with. And then we have a geometry of the detector that will be non-trivial. It's not a perfect cylindrical geometry. It can have sharp edges. There can be cuts. There are other support material, and all that leads to inhomogeneous fields. Now, because the drift velocity drops for both the lower and the higher fields, actually around the peak region, the drift velocity is stabilized. And that's a desirable feature. So in the simplest detector design, the gas choice, would be to look at your desired field strength and then to add a quencher that absorbs both the photons and also stabilizes the drift velocity. There are different examples here, methane, ethane, and isobutane with slightly different behavior. But all of these stabilize the drift velocity because it falls for low and for high field strengths. I've written this here, so we can, the quencher has a dual purpose. It removes the photons and it stabilizes the drift velocity. Now, krypton and xenon have a very short radiation length, which makes it disadvantageous for tracking detectors because the incident particle loses too much energy. I mean, it depends, of course, always on the geometry and on the energies of the detector and the incident particles, but typically you don't want to stop your particle. You just want to measure its track. You want a high ionization yield, but that high ionization yield should not completely change it should not absorb the particle, change its trajectory too much, or lead to large multiple scattering, because we've seen in Mollier theory how this degrades the resolution of position and momentum measurements. But krypton and xenon can still be added for photo detection because of their high probability for pair creation above the material dependent threshold. Now, that's only the absolutely basic design criteria. This is how one would start with. There are other design criteria that we will look at when we discuss the wire detectors, like polymerization, which is actually the biggest problem, that after a few years of operation, polymers form around the wire. And then, of course, toxicity, cost of the gases are also important, sometimes even driving the detector design. So let's look at detector applications. We start very simple with the Geiger-Müller counter. Geiger-Müller is not used in high energy physics, except for the people who operate the detectors at hadron colliders, because they do not want to expose themselves to radioactive fields. Geiger-Müller detector is used to detect radioactive radiation. The characteristic is that it's operated at a very high electric field, a small volume. So a charged particle goes through, causes an ionization signal. The ionization signal produces a streamer, so an avalanche forms and extends. And because of recombinations, photons are created. We've discussed all these aspects. Photons are created, they travel through the detector, hit, for example, hit a wall or a cathode or a gas molecule of a different type and produce secondary avalanches. So at the end, these UV photons spread also transversely through the electric field. The electric field is here from the wire to the cylinder, so in radial detection, and the discharge is, after a very short formation time, is no longer localized. Avalanches are created everywhere. The total charge is completely independent of the primary ionization, so this large-scale discharge is triggered and then proceeds. It stops only when either the power supply is turned off, but typically the voltage is supplied with a capacitance, and if the capacitance is depleted, then the discharge stops, and therefore the time scale of the Geiger-Müller counter is adjusted by the capacitance, the R, the 1 over square root RC of the power supply. Gas amplification in Geiger-Müller counters are 10 to the 8 to 10 to the 10. It depends a little bit on the gas mixture. But these are counting operators, and they have a very long dead time, because the whole gas volume is after the capacitance has been depleted, the whole gas volume is still filled with ions. Those need to be absorbed, and then the capacitance has to be charged again. So electrons are collected quickly. The ions create the plasma tubes that are then so typically that's indicated by these bubbles close to the anode wire, and the ion drift is millisecond time scale, which is not applicable. This just does not work for typical high energy physics operation. The discharge has to be stopped in all the gaseous detectors. On a somewhat shorter time scales of the stopping of this discharge are the spark chambers. Spark chambers are used for, let me show you this, mostly used for outreach purposes. Beginning of the century, spark chambers, the muon was detected in spark chambers, but in the second half of the 20th century, I'm not aware of the usage of a spark chamber for physics purposes, except for maybe creating physicists, because if you show this to children, and even to myself, is very impressive. You can see individual particle trajectories going through the whole detector. Of course, you cannot detect all angles. This geometry selects the tracks that are preferably orthogonal to the plates. But nevertheless, if you've seen a spark chamber, it's nice to look at it for a few minutes and to confirm to yourself that everything we're doing is actually in reality and not just on some computer screen. So a spark chamber consists of parallel plates. There's a gas, and spark-like discharges form across the path that's composed of the individual ionization tracks that are left by, for example, in this case, a muon. The discharge has to be stopped. There is a charging charging resistor that reduces the high voltage, so the time constant of the resistance that charges these parallel plates and the capacitance must be long enough to allow all the ions to reach the cathode. So we're talking about 10 milliseconds or so. One way to reduce the time is to briefly change, or to quickly change the polarity. That helps in reducing the time of clearing the chamber, because the ions created close to the anode are then absorbed very quickly. That's a common mode of operations for spark chambers. As we said, these are outreach, but you should know how they work, because at the Lange Nacht der Forschung, this is what we show. The simplest application, or an application of a simple detector that's close in spirit to the spark chambers, are the so-called streamer chambers. A streamer is like a spark. However, there's a quencher gas, a large amount of quencher gas mixed in the gas volume, so that the signal dies out very quickly. The streamer chamber is is operated in pulsed operation. The pulsing of the voltage allows a short time scale, factor 1,000, so 10 microns or so. Okay, 10 microns is a beginning of time scale of where we can where at high energy physics experiments we can begin to operate, not for general purpose detectors, but for special purpose detectors. These streamer chambers can be fabricated very cheaply. So here's an image. There are rectangular tubes. There's a simple anode wire in those. The rectangular tubes have inside, they have a metallic coating, and a high voltage is applied in pulsed operation. And then there are X and Y strips on top of these simple plastic tubes. And the signal is then collected from the strips in X and Y direction, and it's and that signal is influenced. So you have a streamer that's like a spark discharge quenched by methane or ethane, appearing briefly because of the pulsed operation, and then you have an influenced electrical signal in the electrically otherwise disconnected Y and X stripes. You can imagine that that type of detector is not expensive to build. These are just plastic rectangular tubes coated with high resistivity but still electrically conducting cathode surfaces that you then connect to a standard pulse power supply. So these are streamer chambers, sometimes used if very large detector volumes have to be filled and you don't have enough money. However, we have to move to particle physics detectors, and we start a little bit historically, and because the multi-wire proportional chamber comprises many of the design criteria that we discussed so far. So think of the streamer chamber here. This is all of these volumes here. They are separate. Imagine that you remove the middle walls, then you're left with two cathode plates, and with anode wires. Here they run perpendicular to the screen plane. We have anode wires in some distance d from each other and in some distance L from the cathode. So the typical electrostatic potential in a multi-wire proportional chamber looks like this. As the name indicates, multi-wire proportional chambers have multiple wires and they are run in proportional mode. So avalanche formation takes place. These were the first electronic detectors in 1968, with a well-deserved Nobel Prize in 1992 for George Sharpak, because these were the first detectors that were connected to electronic readout. So no photographic plates. First electronic detectors. The diameters of the anode wires in such detectors are in the 10 to 50 micrometer regime or so. We used 10 in the example above. The distances between the wires can be large, 1 to 5 millimeter. Each wire can be connected to an amplifier, and it's ran in proportional mode with amplification factors of up to 10 to the 5. The particle rate that can be tolerated by such detectors is 10 or so, 10 kilohertz per square millimeter. You have one problem. The problem is that the wires are in parallel, and hence you have only one-dimensional spatial measurement. If you know you know that the avalanche formed close to, or an avalanche formed close to a given wire, you only know one coordinate. You don't know the other coordinate or a third coordinate with 3 spatial coordinates. And hence, at least to have a 2D measurement, one uses consecutive layers of multi-wire proportional chambers rotated by 90 degrees. And then one can measure the full track. Now, in multi-wire proportional chambers have gone out of use. They are now mostly replaced with drift chambers that allow a better resolution, but still it was an extremely important step in detector design to basically remove, take such detectors, wire detectors with a single wire inside the volume, put all those wires together in a single volume and have it attached to an electronic readout. Operating these detectors in proportionality mode improves the position resolution. Why is that so? We can do a small calculation. Let's assume give me 1 second. Oops. I will calculate this. I will calculate this after the lunch break. Yeah. One second. No, that's not. I have it here. Let's assume we only have, we don't run in proportionality mode. We only know which anode wire has fired, but we don't have any signal strength. So let's say, if you look at the screen, let's say this wire has fired. So we can assume that the signal was somewhere close, within half of the distance to the next wire. Let me change color. We can now compute the variance of this measurement. The variance of this measurement is, we're going to discuss this in a little bit of detail when we talk about statistics, but the variance of this measurement is the expectation value of the measurement minus the expectation value of the measurement, which is called the residual squared. So the variance of the measurement is the expectation value of the quadratic deviation. And we have to assume a uniform, distribution for the probability of the distance x where the incident particle went through. So that means let me make a drawing here. If that's our wire, that's half of the distance to the next wire. Our assumption on the probability of the position of the ionization signal, let me sketch it here. F of x is a constant, and it's 1 over a. That 1 over a is just a criterion that the total probability from minus a half to plus a half, that it integrates to 1. I should, dx. I forgot the differential, but that doesn't matter. Now, if you compute that for the uniform distribution with a parameter value of 1 over a, you get an integral of minus a half to 2 to a half dx of x squared times 1 over a. That's because the expectation value itself is 0, so the x squared is the only thing that's remaining. And that's a polynomial integral. And its result is a squared divided by 12. And that means the resolution is a divided by square root of 12. That means if we only know that this wire fired, then we have to assume a uniform distribution of the probability of where the particle actually went through, leading to a resolution of the distance parameter d divided by square root of 12, which in this example is 500 micrometer. Now, because Charburg operated his detector in proportional mode, you have a large ionization signal where the track is closed, and you have a faint ionization signal where the track is a little bit further away. And this allows you to interpolate, and this interpolation gives a resolution that's a factor 10 times better. So we have a position resolution that's a factor 10 better because we're operating in proportionality mode with electronic readout. Moreover, the proportional mode also reduces the dead time because the signal is smaller, but that's only the third advantage. Now, any particle physicist will jump in his chair if the resolution can increase by a factor of 10. That's just enormous. And it's only the operational mode of these detectors. So this is a huge jump forward. You can achieve 50 microns with 2 millimeter spacing. That's very large factors. And now we've also learned a little bit of statistics. We computed the variance of a uniform distribution, and it is square root of 12. It's a factor of square root of 12 less than the length parameter of the uniform distribution. So these are the multi-wire proportional chambers. The gas mixture that's used is oftentimes so-called magic gas mixture. I only mention it because it's a typical application. It's something to start with. So one uses large signal argon, 75%, with 24% isobutan for faster quenching, and then a very small electronegative add-on, in this case freon, that causes a fast decay of the signal. Freon is electronegative. It absorbs signal. It's used in small quantities to lead to a fast decay. So these very rough mixtures are frequently used in these large volume multi-wire proportional chambers. They can be improved very, very easily to resolve the problem that they only have a one-dimensional measurement. One can just cut the cathode plate into cathode strips and collect an influenced not influenced, and I'm sorry, and collect the ion signal at cathode strips. One collects the ion signal, it's not influenced. The multi-wire proportional chamber had this problem that the cathode consists only of one plate. One can segment it and then thus get at least a coarse measurement of the second coordinate. So there are images here that show this. We have cathode strips that give a cathode signal from the ions. These CSCs are used in the CMS detector in trapezoidal panels. There are 6 of such CSC layers on top of each other. They are used in the end cap. Argon is used with a CO2 quencher. These are the main muon detectors in the end cap. You see, these are very simple detectors. They fill a big volume. These are compromised detectors, so they have reasonable spatial time and triggering capabilities. They are not, in the sense, racehorses, let's say, that are tuned to one specific purpose. They are not optimized in one aspect. They cover the CMS muon end caps, and they cover a large area there. Think of, I don't want to go back now in the slides, but I've shown you the CMS detector. These are outside in the end cap wheels. Trigger applications are possible with CSCs. Tracking is possible. The spatial resolution isn't great, but if you're far away from the collision point, then a few millimeters or hundreds of microns is good enough. And these are typical detectors that can be used to detect transition radiation. By adding a xenon, for example, one is sensitive to secondary ionization for pair-produced electrons coming from transition radiation photons, and that can turn the CSCs into photosensitive detectors. To give you an idea, bottom right, the charge that's collected at the cathodes has a very from the ions is a very has a very wide, almost Gaussian distribution. The avalanche, in contrast, is only extends only the small area very close to the wire. Okay, let's move to the next detector concept that's equally simple. This one does not have wires. It is the resistive plate chambers. Resistive plate chambers also falls into this category of rather simple detectors for rather large volumes, typically far away from the interaction point where you want to instrument a large volume, and you don't need too many, you don't need too high granularity. So there is a gas gap typically in the millimeter or sub-millimeter regime. 0.3 to 2 millimeter is what Karl-Franzens says. These resistive plate chambers are usually operated under normal pressure. They have readout strips at the top and the bottom, which are electrically insulated from the voltage supply. So there's a voltage supply that creates the E field, the electric field. We have the ionizing particle, and avalanche formation. There's no wire here, so avalanche formation is started and induces, so creates the signal according to the Shockley-Ramer theorem, which means that one needs high self quenching, because otherwise the discharge would be continuous, and the operational characteristic is very high amplification, typically in the avalanche, or if the quenching is large enough in the streaming mode. These are cheap detectors. Spatial resolution is only millimeters. It depends a little bit on the geometry, of course, of the readout chips. Now, because the mobility the mobility of electrons is high, what's limiting is the mobility of ions, but because the detector is very thin, the timing resolution is actually quite good. One gets to a nanosecond or so. The rate capability is, of course, limited. I'm sure you understand that you cannot tolerate many particles per readout strip, because you stop being able to tell apart the individual hits, and that's when the detector becomes useless. The rate capability is around 100 Hertz per centimeter squared. That's tolerable far away from the interaction point at the Hadron machine after shielding, when we're only dealing with a few particles and mostly muons. They are, however, excellent devices for triggering detectors because of their operation mode in the avalanche regime. So you know that something has happened if you see multiple consecutive hits in resistive plate chambers. In particular, the operation can be stabilized by so-called multi-gap RPCs, and that's the common way RPCs are used in contemporary energy physics particle detectors. One has floating inner gates. That means they don't have their own power supply, they're floating. But because of current conservation, if you have a discharge running from the top to bottom and you need to run through these floating inner gates, you stabilize the current, because the current needs to be conserved across now these smaller gas gaps. That stabilizes the discharge, which is of course much more dynamical and much more non-linear and also much more angle dependent in the case of a single gap, which improves timing resolutions down to 20-50 picoseconds. And that's actually excellent. 20-50 picoseconds is excellent timing resolution and can therefore be used in time of flight detectors, which is, for example, done in the Alice experiment. RPCs are also used in the CMS detector, by the way. Good. These were the cheap detectors. After the break, in half an hour, we talk about drift chambers. And we enter the more fancy regimes of gaseous detectors. I now stop, if I can find my mouse cursor, I stop the recording.